Okay, let's look at some examples with cylindrical components. Some kinematic examples. So suppose we have a particle and we want to determine the magnitude of the resultant forces acting on a 5 kilogram particle at t equals 2 seconds. Here you know that the r changes in time as 2t plus 10 and theta changes as 1.5 t squared minus 6t. Okay, well, we can start out like we did back in the kinematic situation with r, and it's 2t plus 10, so r of 2 is going to equal 4 plus 10 is 14, and then r dot equals 2. So r dot of 2 is equal to 2, and then r double dot is going to equal 0. So r double dot of 2 is 0. Okay, so let's also do our theta while we're here. So theta is 1.5 t squared minus 6t. So theta of 2 equals, this turns out to be minus 15, and theta dot equals, actually that above is minus 18. Theta dot is 3t minus 6, so theta of 2 equals, it's going to equal 0, and then theta double dot equals 3. So theta double dot is constant at 3. Let's draw our free body diagram. So we have some force in some direction. We'll just call it R. Don't know which direction or the magnitude of that, but we do know that we want to make this equal to some theta. Acceleration times mass. So this is an a theta. There we go. And then some mass times acceleration in the r direction. And recall, we have these relationships for the acceleration in the theta and r direction. So then r in the r direction, if we were going to sum forces in the r direction, then we would end up with this relationship where on the left you have the forces acting, and then on the right you have mass times acceleration, and then we can put in values of 5 kilograms, and then r double dot is 0, and we subtract off 2 times theta double dot, or 2 times theta, or we subtract off r, we subtract off r times theta dot, and theta dot here we see is equal to 0 too. So this term is equal to 0. And then if we were to sum forces in the theta direction, we're going to have an r theta, and that's going to equal mass times r. Without a dot, r theta double dot, so it's this relationship, r theta double dot minus 2 r dot theta dot, and that equals 5 kilograms times, so we have 14 times 3 up here, and then we subtract off 2 times r dot would be 2, but our theta dot there is 0. So that portion leaves. So what we're left with is 5 times 14 times 3. And that gives us a final resultant force of 0 in the use of r direction plus 210 in the use of theta direction, and that is in newtons. Okay, next we want to solve this relationship where you have a rod, a pinned rod here, and vertically up 0.5 meters from that is a surface here with a ball on it. I'll draw the surface a little better with a ball on it. And this rod contacts the ball. So theta is in this direction, we'll define, and theta dot is at 2 rads per second constant. And we want to find the normal force on this rod by the surface and the force of, well, the normal force on the ball from the surface and the force by the rod on this ball. So let's draw our free body diagrams. So I'm going to start over here. So we're going to have a radial acceleration in our inertial effects over here. Mass times the acceleration radial, and then we'll have define a mass times the acceleration in the theta direction here, perpendicular to that. So we're going to end up putting on forces over here, and of course we have the normal force here, and we have so if this is the R essentially touching this, then this force here perpendicular to that hits the ball, that must be our force, and it's in the theta direction. So since we're doing a cylindrical problem, we want to keep things in terms of theta here, our geometry. So we know that this is theta. So we can think, so I can think of this as an alpha maybe, and if I extend this perpendicular down to here, because we're trying to figure out the best way to decide how to set up our components for n, then of course this is 90 here, which makes this theta down here, which puts this angle as our alpha here. And that's what we're kind of interested in, because here's the radial direction and here is, so our n component has these, our n force has these components, and the theta that we're going to want to write those in is down here. So theta's in this direction, r is in our the component in the so theta's here, and this is 90. All right, let's begin analyzing this. Let's start with our r and theta. So we don't have a relationship of r with time or theta with time here, and we don't even have a relationship of r and theta, so we really need to start there. So let's just look at this geometry, and we can say that r equals or let's think of it this way. So if we look at this triangle here that maps out what our geometry is, then we could say that 0.5 over r equals the cosine of theta. There we go. Now we've got r in terms of theta. So R actually is. So the thing is we don't want to deal with, well, it's actually 0.5 over cosine theta, and I don't want to play around with this in the denominator, so what we're going to do is 0.5 secant of theta, which complicates the differentiation. So if r equals 0.5 secant of theta, then, and here we go, the complicated mess here. We'll look this up. The derivative of the secant is the secant tangent, so secant of theta, tangent of theta is the derivative of this, and then of course we have to chain rule it, theta dot. Okay, not too bad, could be worse. Our double dot now is 0.5 again. So now the issue is we have 3 thetas up there, functions of thetas at least, and we have to have product rule 3 times. So let's first do the secant again. So we're looking at the secant of theta, tangent of theta, and then, let me leave this off, and then we have to theta dot, chain rule that. So that's the derivative of the secant of theta, but then we need to multiply it by the tangent of theta and theta dot again. All right, and now the second term we're going to differentiate is the tangent of theta. The derivative of the tangent of theta is the secant of theta. Actually, I'm going to put in the secant of theta here because it's multiplied by, and then I'm going to do the derivative of the tangent of theta, which is the secant squared of theta. And then we have a theta dot chain rule going on there because we got to take the derivative of the inside too. And then we also have to multiply in this theta dot. Let me get rid of this multiplication here. I guess we'll put this in parentheses since it's further away. And then, so that accounts for all these 3 terms again, with the tangent of theta, the derivative. And then finally we have the third term, which is going to start out with the secant of theta, tangent of theta, and then the derivative of theta dot, which is just theta double dot. And yeah, that simply is it. So yeah, that's the complicated equation for r double dot. But it's just a matter of plugging in values and calculating these things. For example, r will end up equaling 0.5774 when you stick in theta of the angle we're interested in, which is 30 degrees. So let me rewrite that. So we'll write it like that, and then r dot of 30 degrees equals, this is what we get with r dot. Now notice here we're going to need a theta dot, and in our problem theta equals 30 degrees, and then theta dot was given as a constant 2 rads per second, which makes theta double dot equal to 0. So we're going to need that to plug into some of these places up here. And we end up with these values. And I'll box them and pull down the free body diagram for reference. And let's begin by summing forces in the r direction. And we end up with this relationship where here this is our r double dot minus our r theta dot squared for the acceleration in the tangent direction multiplied by mass. Okay, let's do theta direction next. And as I begin to do my theta direction, I see that I have my weight term in here, and we forgot to put that in our free body diagram. And like that. Then here is our normal component. And in our first equation, we only have one unknown n. We can directly calculate n. Then plugging n into the second relationship, we end up with our force F. And I went ahead and corrected the free body diagram up above too and added 0.5 kilograms as a mass.